thanks for inviting me to this webinar series. You know, one of the benefits of everything getting locked down is that I could go and give a talk in Singapore from the comfort of my living room here. Like I said, my name is Matt Harrigan. I'm from Google's Quantum Group. Quantum at Google is a roughly 60-person team doing hardware, software, theory and algorithm development up and down the West Coast of the United States. And the work presented here was a real team effort. It was a culmination of all three of these things. Like Demetrius said, my background is in computational chemistry and computational biophysics. I'm a software engineer on the algorithms team in Venice, California, and or my apartment nearby. So it's easy to take our iPhone for granted as a magic box that displays TikToks, but sometimes it's helpful to remember that information is fundamentally physical. Whether that's the position of beads in an abacus, the electrons floating around in a RAM module, or the positions of hands on a clock. These are state machines. The physical nature of these states determines how each of these machines processes information. In each of these examples, the physical representation of information uses principles that were known in the 1800s, which we call classical physics. Of course, the 1900s happened, and science has moved on. We've discovered a new kind of state and a new kind of physical dynamics called quantum mechanics. So the natural question is, can we use quantum mechanics for information processing? And the answer seems to be a tentative but meaningful yes. So quantum computers are probabilistic machines where the states are stored in quantum bits, also known as qubits. Whereas classical probability theory says that each state's probabilities must be positive and sum to 1. In quantum computing, we make a simple tweak. The probabilities can be negative or even complex, and their magnitude or absolute value squared must sum to 1 instead of the values themselves. So this very simple tweak, this new framework has enabled some pretty profound theoretical results from the 90s and early 2000s, showing how a theoretical quantum computer could accelerate certain problems. Recently, the team at Google built a really magnificent device. It's a family of processors named Sycamore. This one in particular was 54 qubits, and we demonstrated that it could perform a contrived but well-defined sampling problem in such a way that it would take a classical supercomputer on the order of years to emulate and produce the same samples. And you may think that random numbers, numbers that are random in a very particular way, wouldn't be worth the hard drives they're written on. There actually is a use case for certified random number generation that the team is pursuing as a follow-on application to this fundamental demonstration. But clearly, there are other applications beyond these sampling problems that really excite the field. So quantum computing is a natural tool to simulate systems which are themselves quantum. This pops up a lot in chemistry and materials research. Everyone knows that factoring is a problem which is thought to be very hard classically, and there's a known quantum algorithm for doing it in polynomial time, assuming a noiseless processor. And there's also a lot of speculating that machine learning could really benefit from the large Hilbert space that you have access to in a quantum processor. But in this talk, we're mostly interested in discrete optimization problems or combinatorial optimization problems. So the first thing to know about these is they're super prolific throughout industry. Everything in logistics, from routing, scheduling, and supply chain management is an example of this. There's tons of applications in finance for portfolio optimization, asset pricing. Many classic machine learning techniques are discrete optimization problems. Image segmentation is one example. And this large industrial relevance has really driven interest in the possibility of quantum enhanced optimization. And the possibility of some sort of quantum enhancement or quantum speedup here has been one of the main drivers for the whole field of quantum information, I'd posit. Despite this sort of historical interest in these sorts of problems in the context of quantum computing, there's been a historical issue, which we'll get to in due time. But let's understand what the problems are we're trying to solve. These combinatorial optimization problems are such that you're given a finite set of objects we want to pick and choose from to minimize some cost function. So one classic example of an NP-hard optimization problem is Sudoku. So you're given an initial configuration and a set of constraints. The constraints are the rules of the game. And you must select from a set of digits to fill each square. So Sudoku is technically NP complete if you allow the size of the grid to scale arbitrarily. NP complete problems come with a built-in blessing and curse. NP complete problems can all be mapped among each other. So the blessing is if you could solve one type of NP complete problem, you can solve them all. The curse is you probably can't. These are very difficult, and exact solutions require exponential time, classically and probably quantumly as well, but there's nothing proven there. So just for the experimental demonstration in this talk, without loss of generality, we'll consider problems where the answer is a string of bits, zeros and ones. This is very natural for us because our hardware uses qubits. At the end, you measure them, and they're zeros and ones. And this is a transformation that can be done for any NP complete problem with polynomial overhead. So there's a very basic prerequisite for doing quantum optimization. And that is you have to make the quantum system feel the problem you're trying to solve. And remember, we're trying to find a set of discrete variables x or bit string to minimize a cost function c of x. So we make the quantum system feel the problem via queries to this cost function that applies a phase to states. You could think of this prerequisite as the quantum computer needs to be able to compute the cost function c of x. And in general, you should have it compute the cost function on all states at once and tag each state with a nice phase that you can exploit through trickery. So all algorithms for quantum optimization have this phasing by the cost function as their challenging step. Grover search, annealing, population transfer, and QAOA. This is sort of the key component, and it makes sense. You have to get the problem in there somehow. And the historical issue that sort of started with quantum annealers like those produced by D-Wave in the mid-2000s and to this day is that they could only realize easy to solve cost functions. They can only phase these states with cost functions that typify problems that are simple to solve with classical heuristics. So annealers certainly have this problem, but recent gate model experiments and demonstrations have fallen into a similar trap of sticking to hardware native problems. Now, we have to get a little bit into the hardware. I'm no expert on quantum hardware, but I do know, once again, that information is physical. So when we fabricate these devices, our qubits are physically laid out in a 2D grid. The Sycamore layout is on the right. And qubits are only coupled to their neighbors. So if your problem has a constraint between 2 bits, you'd really like those 2 bits in the constraint to be adjacent so you can phase the state there. So indeed, in this table of gate model demonstrations of optimizations over the years, as some of these devices have started to come online from Rigetti and IBM and university labs, all of the problems that have been demonstrated have been tailored to the hardware in this way, with one minor exception for a 4-qubit demonstration, which is quite small. This is only gate model approaches. For quantum annealers, every single problem they've solved is hardware native in the sense that I'm using, because that's the only thing they really can do. So to make this a little more concrete, I'm going to introduce a notion here, which I'll call the problem topology. So if your optimization problem has a quadratic cost function, so C is a sum of 2-body terms, each one being a penalty or a reward depending on some weight, Wij. This 2-body structure means that you can visualize the problem itself as a graph with bits and qubits as nodes and connections corresponding to non-zero weights, and the edge weights would be the weights Wij. So when the actual problem topology or graph matches the hardware topology, that's a hardware native graph, and you're sort of off to the races. The physical reality matches the problem you're trying to solve. But once again, it should come as no surprise that these problems are typically not industrially relevant, and they're easy to solve heuristically. So for example, if you were trying to solve Sudoku, well, first of all, you need to map it into a binary problem and then map it into a quadratic problem, which is all something you could do pretty straightforwardly with a little bit of overhead. But what you'll end up with will not be a set of bits in a planar grid interacting with their neighbors and only their neighbors. There will be more complicated structure in the problem. So for this study, we generated random instances both of these tailored hardware grid problems, but also prototypical computer science families of problems that don't match the device. And in particular, we looked at MaxCut and the Sherrington-Kirkpatrick model. MaxCut is itself a graph problem, so its visualization as a graph is incredibly straightforward. We generated a series of random 3 regular graphs. That just means each node has degree 3. And the goal here is to cut the graph into 2 groups where we maximize the number of cut edges. And it's actually difficult as the number of nodes gets very large. And we studied this because this problem has a lot of history associated with it in both the classical and quantum optimization literature. It's really a prototypical discrete optimization problem when you pull away all the fluff and pomp and circumstance. The Sherrington-Kirkpatrick model is fully connected, and this is why we were interested in this one as well. This is as far as you can get from a hardware native problem, as each pair of bits has a term in the cost function, either a penalty or reward. And specifically here, just for completeness, the edge weights we sampled as plus or minus 1 randomly. There's also a nice physics connection. This is a common model system for investigating spin glasses. While annealers can only solve hardware native cost functions, gate model computers, we have some tricks up our sleeve. We could get around these limitations by performing swap operations, which swaps the logical information inside of the physical qubit around the chip. So we can move qubits around. When I say that, I don't mean the physical etching onto the aluminum, but the data within. And there's also another nicety with gate model computers, which is we can compile cost functions with greater than 2-body terms in them as well to reduce some of the overhead, but we didn't investigate that here. So just to be very clear, in this work, we show much more challenging problem topologies at larger sizes and larger circuit depths. And quickly, so everyone's on the same page, make sure we know what we're talking about with an algorithm here. We have a number of qubits, which we'll draw as lines and typically call n. And then according to some schedule in time, we apply operations to these qubits. And these will be depicted as boxes. Usually they'll have labels, but in the abstract diagram here, they're just colored. And the really important thing to note about the current devices being fabricated in our lab and elsewhere is that each operation has a probability of error. There's noise in the system, and there's different ways of looking at the noise, but a really useful way of considering noise is that each time you do a gate, there is a potential for error. And in our case, the rule of thumb, there's around a 0.5% chance of error after each operation you do. So you can imagine that we're severely limited in the depth of circuits we can do, AKA the number of operations we apply. So just to be clear, the depth in this example is 2. As I said before, we're also limited in which qubits we can interact with each other. And then the final thing in near-term quantum algorithm is you measure your qubits at the end and they turn into bits 0 and 1. And you could do whatever classical post-processing you want on those bits. So this noise severely limits the depth of circuits we can compute on the hardware with the error rates today. So to compensate for this limitation on depth, near-term algorithms that people have just started really thinking seriously about since the early 2010s, they use a variational approach. And the specific algorithm we use here is known as the Quantum Approximate Optimization Algorithm, QAOA. And it is one such variational algorithm. It's designed appropriately enough for quantum optimization. This algorithm calls for the repeated application of 2 unitary operations, UC and UB. Which we'll call, I'll refer to as the problem unitary and the driver unitary. The problem unitary phases states just according to the cost function, as we were talking about before. So this is really the challenging part that creates entanglement in the system, requires 2-qubit or multi-qubit operations, and this is how the problem enters the actual algorithm. The second unitary is the driver unitary, and this serves to drive transitions between computational basis states and is relatively simple to implement with a series of single qubit X rotations. And I've drawn big parentheses around these 2 unitaries raised to the power of p. We have this hyperparameter p where you oscillate between these application of these 2 unitaries p times. And since this is a variational algorithm, we have freedom in the problem and driver unitaries. And in fact, the freedom is the strength with which we apply these unitaries. By convention, each layer has 2 parameters, sometimes called angles, gamma and beta. Gamma parameterizing the problem unitary and beta parameterizing the driver unitary. We run the quantum circuit with a particular choice for the gammas and betas. We sample many bit strings from the quantum device. In this experiment, typically we would sample 50,000 at a time to estimate some objective function. Here, the average value of the cost function that we see from the bit strings we're getting out, which, since these are NP problems, is easy to do classically. Once you have bits, you can figure out how good they are. And then we pass that through a classical gradient descent type optimizer to suggest new parameters, which, so new gammas and betas, which will improve the average quality of solutions. So this is the general loop we'll run. So for p equals 1, just to be clear, there are only two parameters, sort of gamma 1 and beta 1, which I'll just call gamma and beta. And we can actually plot the full parameter landscape to see what it looks like. For larger p, there are 2p parameters. And in this now high dimensional space, you will have to use one of these classical optimizers to find the optimal settings. You can't do a full grid search. And just so we're clear on some more intuition about sort of why and how the QAOA works, historically it was developed from an adiabatic type approach, where if you take p to infinity, this is a digitized version of annealing, where the problem unitary is evolution under the cost Hamiltonian or the problem Hamiltonian, and the driver is evolution under the transverse field, and the variational parameters set at p equals infinity encode some sort of annealing schedule. Of course, we cannot run p equals infinity. We're typically limited to p less than 10. So the variational freedom there will allow us to deviate from just a digitized version of the annealing approach. So executing the driver unitary is fairly simple, but to execute the problem unitary for a non-hardware native problem, we have to do a significant amount of compilation. Compilation, I like to think of as in two steps, routing and gate synthesis. So we'll walk through an example of how we compile the problem unitary for this 17-qubit fully connected model, which we executed in hardware. So every node needs to talk to another node. So we implement a series of swap operations in this brick-like layout here, where if you trace through any given line, you'll see it sort of percolates from one side to the other. And the logical information stored in these qubits bubble past each other. In fact, if you do n rounds of this, every pair of qubits interacts exactly once. Fans of classical sorting algorithms can see that this is a parallel version of a bubble sort if you start with a reversed list, just a little nice thing. But once we have this brick layer pattern, we need to understand what these purple boxes actually are. And in particular, since all of the components in our problem unitary commute with each other and commute with the swap operation, we can simultaneously apply the ZZ phase according to the problem for the particular logical pair we're working with at any given slice, along with the swap operation. And we could consider this one composite operation. So this purple box is doing something rather complex. It's doing what we want for a pair of qubits and swapping the qubits so that it will be in the correct location for another pair to be activated later on. And of course, in our hardware, we can only natively implement some gates. We have a lot of freedom in what single qubit gates we could execute, but the native 2-qubit operation is currently tuned up is a square root iswap gate, which you can find in some textbooks in the more advanced section after you've gone past CNOTs and such like that. Or the operation in this green box denoted as SYC, the sycamore gate. It's an inverse iswap gate with a pi/6 conditional phase. It's very natural for our particular hardware to evolve under this gate, and this is just the Hamiltonian we've printed onto the circuit board.
Matt, if I can interrupt, give you a second to breathe as well. But so what is the natural interaction in this specific one? Is it between your superconducting qubits? Is it XY interaction? Is it ZZ interaction? Would do you have to, do you know that, or
it's a complicated mixture of XX, YY, and ZZ. So this the Sycamore gate it is this I-swap gate, which is an XY interaction, along with a pi/6 conditional phase, which is has more ZZ character.
All right, so that happens. You just naturally you own the coupling and you naturally evolve it, and you get that basically.
That's right. So for in the quantum supremacy paper, they took this sort of one step further and just let the system. They found exactly what the natural 2-qubit interaction was, which deviated a little bit from the pi/6 conditional phase. And there was actually a different 2-qubit interaction for each pair of qubits that was used in the random circuits. Of course, the randomization came from the single qubit freedom. But I think it would have been fair to question at the time, like, this is a very strange thing to do in a computation.
Yeah.
So one of the nice results from this work is that we could tune this up a little bit more, nail in exactly that pi/6 conditional phase, so we know what interaction we're implementing. And we could show that it's not just in theory, almost any 2-qubit gate is universal. We can actually constructively make pretty much whatever 2-qubit gate we want, given 3-ish applications of the Sycamore gate. So that's right. This is it has a pretty unusual form, but it's simple enough to compile our desired interactions. So in particular, you could do this composite ZZ swap operation with 3 rounds of Sycamore gates and interleaved single qubit gates.
Okay, good, thanks.
Mm-hmm. Yeah, so that's the routing problem. It is sort of solved by laying out these purple bricks in this nice way. And then we have to actually synthesize this operation that in theory we'd like to do into things we can practically do, which is just multiplies the depth by 3 here. So now we'll look at some results. First, we'll consider what people usually look at, which are these hardware native problems. So all of this work was run on a 23 qubit Sycamore chip, not the full 54 qubit one. It was a different fridge. So this is all 23 qubits that we had available to us with random couplings between them. And here we're showing the parameter landscape for p = 1. So remember, there's only one beta and one gamma angle, which are the y and x axes here. And then the color z-axis is the average quality of solutions you're sampling from the device at that parameter setting. On the left is a noiseless simulation of what we'd expect from the QAOA at p = 1. And you could see there are hills and valleys in various locations where parameters work to give you good solutions or mediocre solutions or really bad solutions. And on the right is the actual data from the device. So we just did a grid search over every possible over a grid of beta gamma settings to get what is a remarkable correspondence for a 23 qubit real problem here. So you can immediately see all of the peaks and valleys are in the correct location. The contrast is very good. There's some slight streaking you could see, sort of rasterization effect from the fact that this experiment takes quite a bit of time and the system may have drifted. But what's key is with this visualization is that we could show that classical optimizer here using something called model gradient descent initialized from the parameter settings at the red square, can quickly find the maximum, whose theoretical position is shown with a blue star. And this shows that the variational aspect of this algorithm is working quite well. And this sort of world-class result is possible due to the low error rates and the low crosstalk on the device, which I think is a really key to moving these demonstrations beyond small 4-bit problems. And I will mention that there's a developing tradition in using these plots, I think because they're very pretty, but you could find several examples in the literature. The sort of previous best for a hardware native problem was at n equals 20. So this is sort of similar to that. And they provide at a glance a quick diagnostic view of whether the system's working properly.
Matt, there is a question from the audience.
Sure.
If the right-hand side plot heat map, is it a simulation or experimental grid search?
The left is a noiseless simulation and the right is real data from the device. So yeah, we ran this using Circ, our open source framework for writing quantum programs. We ran it through an alpha version of a cloud interface. So this is really like how you would use a quantum computer in practice. The hardware team has some automated calibration that tunes up the device once a day-ish or even less frequently. And then you can just submit programs to execute on the cloud and it returns the results. So yeah, the right is definitely experimental results.
Yeah. One small follow-up, and then we same person, Philip. What is the grid size?
That's a good question. Details in the paper, I think this is a 50 by 50 grid. It's pretty fine. You could squint, but you could see the pixels.
All right, thanks. Good. Cheers.
Yeah. It's a slightly different story when you move to the much more complicated Sherrington-Kirkpatrick model, even at a more modest problem size of 11 bits. Remember, our depth now scales with the problem size due to this compilation, due to this swap network we have to implement. The hills and valleys aren't as sharp as before, but the classical optimizer, the model gradient descent, is still able to climb uphill and find the correct bit strings. A little bit of the contrast is washed out, but again, this is sort of best-in-class performance for very deep circuit. The previous largest complete graph demonstration was maxed out at n equals 4. They have one of these landscapes for that. Which is nice to see other people doing non-native graphs in their demonstrations of QAOA. But the quadratic nature of this problem means that n equals 11 is actually much more challenging than n equals 4. So we could look at this from a different axes. We're going to move to a regime where we compute the optimal angles classically, sort of offline, so that we could run more instances. We could compare the performance of many random instances at a variety of problem sizes and circuit depths. So bear with the color on this slide for 1 second. Here we show the performance on the hardware grid problem up to a maximum of n equals 23, and this is at a p depth of 3. As you move up in the problem size after about 10 qubits, the performance levels out. Higher is better. The upper square points, the upper band of points, are simulated, and the lower points, which are circles, are experimental results. So there is some gap in performance due to the noise, but it seems to not be getting worse as you make these problems arbitrarily large. So this sort of gives us confidence that it makes sense to try extending this demonstration out to larger and larger problem sizes. And again, or I should say the fact that the error is sort of independent of problem size is expected from the very simple compilation of these hardware native problems and the low degree of the graph. But once again, only assuming a local error model with no crosstalk. So this is another testament to hardware behaving pretty much as you'd expect. It's a different story when we look at the SK model on a similar plot. Whereas the noiseless results are sort of comparable to what you'd expect in the hardware grid problem, the additional compilation means that now our performance actually scales with the problem size as the actual depth starts to get very, very deep due to this compilation. So like I said, we had a 23 qubit grid to run these on. We ran Sherrington-Kirkpatrick up to a maximum of 17 qubits, which is the largest line we could snake on the device. So this is still p equals 3, which means these are very, very deep circuits. So we're seeing relatively good performance at modest problem sizes. You could see you're definitely getting signal up to 11, 12, 13 qubits, and it doesn't collapse to completely random results until 17 qubits or higher. But clearly the performance is degrading with the problem size, which means that scaling up this more challenging problem, we might run into difficulties. And if you recall, we expect industrially relevant problems to definitely not be as easy as the hardware grid problem. Maybe they won't be as difficult as the SK model, which again is sort of the worst you could get, but it'll definitely be somewhere in between. And this highlights the need for some sort of theoretical advancement in if we really want to consider QAOA as a viable near-term intermediate scale approach to doing quantum optimization. And just not to belabor the point, but I have some numbers up here on the right side that put into relief the difference between the complexity of implementing these two problems of similar size. The hardware grid problem requires 24 layers of 2 qubit gates, whereas the Sherrington-Kirkpatrick model requires 153 layers of 2 qubit gates at p equals 3, which is over 1,200 2 qubit gates. And we're still seeing sort of non-negligible performance, which is fantastic. We can also scan over this depth hyperparameter p. Without noise, higher p is always better. Remember that as p goes to infinity, this should always give you the exact correct answer. And indeed, the green curve here shows that on average you get better quality results as you increase p. But with noise in a real environment, there's a trade-off. As you go to higher depth, there's more noise, which degrades the quality of your solution. And what's really noteworthy about this demonstration is that for the first time, we see, thanks to the hardware grid simple compilation and the high quality of the device, the performance actually peaks at p greater than 1. Now, again, remember that if we are serious about getting some sort of quantum advantage in the near term from QAOA, we're going to need to be able to scale this hyperparameter to higher quality solutions. So we see the average performance peaks at p equals 3. We can look at, this is averaged over several hundred random instances. And if we look on a per instance basis, over 50% of them do best at p equals 3. Some of them you could push to p equals 4 and still see an improvement. And the previous best demonstration of this effect was just showing that the solution quality at p equals 1 is equivalent to the solution quality at p equals 2, i.e. it doesn't make things worse. So it was nice to see tentative steps towards our ability to tune this to crank up this hyperparameter to improve the quality of solutions. So in summary, we did a demonstration of QAOA on the Sycamore family of processors. It showed that there is nice qualitative agreement between the simulated and experimental landscapes. Everything is behaving as expected. We can use what may seem like a very non-standard gate to do an actual computational algorithm of interest. We could do a classical outer loop optimization on this variational algorithm to find optimal parameters. And we showed that these hardware native problems that people seem so fond of for previous demonstrations show some desirable features. The end-independent noise permits good performance at large sizes. And the simple compilation means that you could go to higher P to provide higher quality solutions, at least on our device. But real problems will likely require more compilation, which can lead to challenges in scaling up. And we saw this with the SK model. And there's also this nice emerging tradition of using QAOA as a holistic benchmark for quantum devices to get a sense for how they'd actually perform on multi-qubit algorithms of interest. And in general, we'd love to see more groups doing non-native graphs and solving them. Thank you so much for listening, and I'm happy to take a whole bunch of questions and discuss.
Thanks, Matt. Virtual thank you. And
virtual round of applause.
Yes. So we're open to questions. One is, again, Philip, no surname. It would be good to have your surname as well, Philip. What noise model did you use? I'm just repeating the questions. I'm not changing the...
Sure.
Yeah.
So for all of the simulations that I've presented in this presentation, all of the simulations are noiseless. So this upper band of square points is noiseless simulation, which just shows that at p equals 3, you can't get perfect bit strings back every time. This is the quantum approximate optimization algorithm. So at p equals 3, it dips below 1.0, which would be the perfect result. So in this presentation, there's no noise model as such. All of the data presented is experimental. In general, we are very interested in what sort of noise model fits our device. I don't have these plots handy right now, but one of the interesting things to see while running this experiment is that a depolarizing noise model fits the data pretty well, all things considered. The system is fairly well behaved.
Okay. Any other question?
Okay. Can I ask a question?
I would prefer on the chat, but
okay.
But you can, if you state your name and affiliation, maybe we can also take it online as you started. Is it Rahul? Is you Rahul? Okay, sorry, I didn't see.
Yeah.
Go ahead.
Rahul, yeah. Okay, thanks. So, okay, I'm just trying to understand, like, if there are some concrete theoretical questions that we can crystal out from here. So, in I think you talked about these native graph problems versus not, right? So, like if you go, I think at the beginning, you basically, you know, for each input x, you have a cost function c of x, right?
That's right.
So here you define your c. Okay, sorry. So you're calling it c of x, but I don't see an x here, but I presume it's z on the slide, right?
Yeah, I'm playing it a little fast and loose with my variable names.
Yeah, right. So it's c of z out there. Yeah. So
as written here, c is an operator. It's a quantum mechanical operator that you could take an expectation value of.
I see. Okay. So you're not taking x as a classical input, is it? And you're not thinking of c of x as a function of a classical input? I mean, usually in optimization, what we do is we have it's a function from you know, a classical domain to a classical domain, right? And we're optimizing it, right?
Yeah. So, right. So C of X, you can write it purely classically. You can implement it in NumPy or whatever, and X will be a bit string, and it will return you a number.
Exactly.
In order to implement this in QAOA or in any quantum algorithm, you transform it to this operator form, where it's written in terms of products of poly Z operators. If it's only poly Z operators, then it's a classical cost function. You could use things like QAOA for for quantum cost functions, but here we looked at all entirely classical ones.
Right.
So
Yeah. So once you have a classical function C of X, right? Okay. So is it that you want to put the thing in the phase? You want to put -1 to the C of X, or e to the
yeah, that's correct.
e to the minus I. Yeah.
We want to phase the computational basis states by their cost function value.
Okay, all right. So suppose you had a circuit which took, you know, your summation x axx 0 to summation x c of x. So suppose instead of putting c of x on the phase, it was just writing c of x on a register next to it.
Sure.
Okay. Now as long as your c of x is easy to compute from x, then it's not so difficult to. I don't know whether it is or not, to put C of X in a register next to X. Is that easy or is that difficult? Or?
Well, that's certainly out of the realm of possibility for near-term devices. When you have these two large registers, that's like super non-local operations you have to start doing.
Actually, you know, the computation from X to CX is classical, right? I mean, you take a classical circuit, right?
Oh, I see. Well, why would you want to do that though?
No, because you want to put it in the phase, so it can be done in a two-step process. One is first write C of X by the side of X, and then later put it on phase. You know what I'm saying? I think what you're doing is you're trying to directly put it on phase, right?
Yeah, I mean, the advantage of doing it via this operator is that you could phase every 2 to the n computational basis state with one application of this problem unitary.
No, I understand, but I think this is probably restricting you to certain graph topologies and so on. I'm saying, suppose we take the following approach, right? We take any cost function C of X, which is easy to compute, okay?
Mm-hmm.
Let's say it's efficient. Classical computation from X to C of X is easy, let's say, okay?
Mm-hmm.
Now, I mean, typically cost functions are easy to compute. I mean, it's the optimization which becomes difficult to do. But the cost functions are typically easy to compute, right? So, so now from X, pardon me?
Sorry, that will depend on the problem.
Sorry,
just
to avoid maybe, if you could...
easy to compute. Sorry, I didn't get it.
Sorry, wait. So I would like to avoid the live discussion. So maybe if we can just focus on this question, so or take it offline. If there are other questions, maybe add them on the chat, because this might be a little bit too long for everybody. So maybe we can just summarize the question. Rahul, what's the...
Okay. So just I was just trying to explore the possibility of first computing C of X, right, and then putting it in the phase. I don't know whether trying to compute.
What are you using as X?
X is going to be your input, right?
I think you are referring, but maybe we can take this offline. I think you are referring to the original mapping from the graph to the cost function here. What Matt is trying to say is that in general, the original mapping is there mathematically, but the hardware, when you go to the hardware, it might require you to have very long range, very complicated terms, which are very hard to implement if I got it right. But maybe it's good to take this offline afterwards. Maybe, I don't know.
Okay, yeah, let's take this offline. If you have some time after the talk, maybe we can just.
Yeah, we
Sure.
can. Any other questions from the audience? There's one by T. Parat. In the SK model, the cost landscape for sufficiently strong quench disorder weights consists of exponentially many plateaus and spurious minima. How did you bypass getting stuck in this spurious minima and search for the global minimum? So he says that the SK model basically, you get too many plateaus and too many minima. Should I repeat the question or?
No, that makes sense.
All right.
So just to be clear, the landscape here is over the variational parameters. And then in terms of actually solving the problem, that's one of the advantages to QAOA is it does, it's more of a global optimization.
Okay.
It is approximate and random. So at the end, you just get bit strings and you have to check to see how well they do. So it's possible that you need to go to extremely large P to overcome some of those problems. But we didn't run into any of that for problems of, 17 bits or smaller.
Okay. Yeah, I think, yeah, exactly. So you might run into this in larger systems, like some sort of bottom plateau situation, but not for this.
Yeah, that's entirely possible.
Yeah.
With QAOA, we have a decent way of initializing the parameters so we don't run exactly into the barren plateaus, but you may need really high P depth to solve.
Yeah, exactly, which is tough to implement. P here was 3. What was in the experiment, I think?
Yeah, so we showed P equals 3 on this plot.
Yeah, okay. Any another question from Ashish? No, this just classically can compute only one point solution, whereas convent you can have all the possible X in one shot. I think he refers to the upper question. Is it guaranteed to produce global optimal solutions? I'm not sure. Is this a question?
So at P less than infinity, it's not guaranteed to do anything.
Exactly, yes. And real experiments.
There's probability weight on every possible bit string, and it does sort of operate in this global manner. But
exactly. And as we say, as we physicists or maybe chemists as well say, experiments happen in the real world, not that in the infinity or thermodynamic limit. So, okay, maybe we can take 2 more questions if somebody has from the audience wants to ask something more. Is there anything else? Okay, if not, let's thank Matt virtually again, and I think we'll see you next week. The rest of the guys, you can register for the rest of the series. There will be more announced soon. Next week will be from our group on some recent theory work on analog quantum supremacy and many-body systems and machine learning. And thank you for joining.